Hello, my name is Richard Carter. This is my final project video, Route Optimization for United States High-Speed Rail. The agenda for this video is to discuss the problem, my assumptions, and research. I will show the method, MATLAB code, final results, and discuss future plans. As a recap, my main objective is to determine high-speed rail routing structure in the U.S. to maximize economic benefit considering speeds of current high-speed rail, magnetic levitation, and hyperloop, given a federal budget. In this problem, I assumed all new rail structures will need to be built and that there are no constraints. This problem is solved as a 0-1 knapsack problem where objects are city pairs. Each city pair will be considered 3 times with high-speed rail, maglev, and hyperloop. The weights are the calculated cost of construction and maintenance, and the value is determined by a valuation equation from America2050.org. A total of 97 cities were considered, resulting in 14,259 total possible objects. The capacity of the knapsack is a given federal budget. To the left is the valuation equation from America2050.org. This group published a study in 2008 suggesting the highest value city pairs for high-speed rail connection based on statistics like ridership, city and metro area GDP, distance, traffic, all done at a rail speed of 150 miles per hour. To the right is the cost calculation for construction and maintenance. Here are America 2050's original value results, and to the right are the new results with updated speeds and data. After calculating new values and costs, the data was analyzed in the Knapsack MATLAB code. Here's the MATLAB code used to solve the problem. I can copy and paste my value and weight pairs from Excel into a MATLAB text file. The MATLAB code reads data from a named text file and sorts by weight. This code shows the dynamic programming loop that chooses the best values, resorts according to weight and value, and chooses again until reaching capacity. Finally, the chosen pairs are published in a text file. Note that with this method, the code often resulted in 2 city pairs being chosen twice for different travel methods. To avoid this, I would run the program, determine repeated city pairs, delete any of the not chosen or lower value counterparts, then run again until I had all unique pairs. Since high-speed rail and maglev are the same cost and essentially the same value, conventional high-speed rail is never chosen. At a lower capacity, the code ran in seconds. At higher capacities, $500 billion, the code took approximately a minute and 6 seconds. When the program is run for all 97 cities at a capacity of $10 billion, this is the result. Essentially, suburbs are connected to cities. At a capacity of $50 billion, we see suburbs and cities start to branch out. Notice our first Hyperloop connection from Portland, Maine to Manchester, New Hampshire. Finally, at a capacity of $500 billion, we see the eastern seaboard almost fully connected with few advancements in the west. The America 2050 valuation equation assumes that high-speed rail will only compete with road traffic. With high-speed rail transportation like maglev and hyperloop, we also need to consider competition with airline travel and add value to city pairs accordingly. To account for this, I added value for the transportation to each city center with addition of value for higher speeds. I also considered each city's airport traffic. Notice that the cost equation did not change. For comparison, here's our new $10 billion run. Not much has changed. Here's a run at $50 billion capacity. Notice the added hyperloop connection between Burlington, Vermont and Manchester, New Hampshire. Finally, the run at $500 billion capacity results in hyperloop connections over longer distances. Quebec is connected down the eastern seaboard all the way to Columbus, Ohio and Jackson, Mississippi. Next for this project is to keep tweaking the cost and value equations to determine the most accurate model. While I was able to delete repeated city pairs if a city pair was chosen twice, the current mode and method does not account for redundant routing. A route may exist from DC to Baltimore and from Baltimore to New York, so a route direct from DC to New York is redundant and less value than another frontier branching or connecting route. This could possibly be accomplished using a tunneling or ant colony algorithm or adaptable knapsack problem where new values are assigned to already connected cities. Overall, a better cost-benefit analysis would determine using this method. Here are my sources, and thank you for your time.